Hi. One of the most important computations we conduct in chemistry involves converting a measurement in one unit to a measurement in a more relevant unit. These simple conversion relationships fill in many of the gaps that we will have in our solution maps. Because we do this kind of math so often, we can save a ton of time and effort if we work hard to master the foundational knowledge presented in this lecture.
I know it's not fun, but it's critical for us first to have a set of conversion factors sitting in our memory banks that we can quickly draw from when we need them. I've listed on this slide a minimum set of conversions I would expect my students to have tucked away in their memory, and I've been careful to identify which conversions are exact and which are approximations. Obviously, we need to know all the SI prefix multipliers, a variety of US customary to SI unit conversions, and time units. I know it seems inconvenient, but until the whole world goes SI, it will be helpful to have a number of US customary units at hand too. And don't forget, we have the derived unit of volume, where the volume is defined as a length unit cubed. The most important SI conversion to remember for volume is that 1 milliliter is exactly equal to 1 centimeter cubed. The most common problem we will encounter is simple single-step conversions. These kinds of conversions are common in a single step or gap in our solution maps. Typically, in these types of conversions, the given number in the problem statement will be the quantity that limits our sig figs in the final answer. Let's look at problems using exact conversion relationships first. Here's the problem statement. Convert 0.267 kilometers to meters. Okay, we'll be overly rigorous and wordy on this particular question to fully show the problem-solving process in action. Obviously, once we get into the habit of utilizing this process, we can assume or even skip some steps, especially for these simple computations. For this problem, the beginning and ending point is easy to identify. We're going from kilometers to meters. I know that meters are much smaller than kilometers, so I expect to get a bunch of meters. We realize we are dealing with the metric length-to-length conversion, so we use our SI prefix table to find our conversion relationship. The prefix table shows that the kilometer multiplier is 1,000, so we multiply a meter 1,000 times to make 1 kilometer. The conversion relationship, therefore, is 1,000 meters equals 1 kilometer. This is an exact conversion, so we know all the numbers in the relationship will have an infinite number of sig figs. We will set up the ratio so that the units cancel to get us from where we are to where we want to be, and write the values in our conversion relationship into the ratio. We compute the value and then adjust the answer to 3 sig figs, knowing the beginning value, which has 3 sig figs, determines the precision of the final answer in the multiplication division computations. The answer is 267 meters, which we write in a way that is not ambiguous, utilizing scientific notation. Finally, we box our answer. Did we answer the problem statement? Yes. We wanted meters. Does our answer make sense? Yes. We expected to get more meters than kilometers, and we did. Do we have the right number of sig figs and included units? Yes. 3 sig figs, and the answer is in meters. Did we learn anything from this problem? Well, I sure hope you did. Let's look at a couple more problems. 34.26 milliliters is equivalent to how many microliters? Again, we will use SI prefixes. We see that milliliters and microliters are different by a magnitude of 3 or a factor of 1,000, and microliters are smaller than milliliters. Notice our given value has 4 sig figs, so the answer better have 4 sig figs. How many centimeters do we have if we measured 53.00 inches? For this problem, we use our US customary to SI unit conversion of 1 inch equals 2.54 centimeters, an exact unit conversion to get to the answer. This next example demonstrates the use of an approximated conversion relationship. The problem states 4.56000 times 10 to the second liters is how many quarts? From our conversion table, we have 1 liter equals 1.057 quarts, but we know this is not an exact conversion, and the relationship has 4 sig figs, and it's less precise than the original given value, which we see has 6 sig figs. Now we have a choice to make. We can calculate a number using our conversion factor and limit it to 4 sig figs based on the conversion relationship that we have in hand, or find a better conversion factor that has more than 6 sig figs so we don't lose any precision when we convert our given quantity to the final value in quarts. So I look for a better conversion factor, and I find one on the web. Okay, I only need 7 or 8 sig figs, so I'm going to cut the conversion relationship to 8 sig figs. Now we have a conversion relationship that has enough sig figs to ensure that I don't limit the final precision of the computation to a value with less than 6 sig figs. The final demonstration involves conversions with derived units. These are simple but critical calculations when we want to convert one class of units, such as length, to another unit class, such as volume. 2.57 milliliters is how many centimeters cubed? This problem asks us to convert a volume unit, milliliters, to the length unit, centimeters cubed. We can see this conversion is simple, since 1 milliliter is equivalent to 1 centimeter cubed exactly. Many times we will simply assume 1 milliliter is 1 centimeter cubed in conversions in most problems. Now here's a similar example. 5.678 times 10 to the third joules is how many meters cubed Pascal? This converts an energy unit, joules, to volume pressure units, meters cubed pascals. Again, this is an easy conversion because the definition is 1 joule is exactly equal to 1 meter cubed Pascal, so the conversion is direct and efficient to apply. The natural progression in complexity is to require more than one conversion relationship in our solution map to solve the given problem. Let's do a rather straightforward computation. Convert 5.00 times 10 to the third yards to kilometers using the conversion relationships shown in our tables. Our starting and ending points are obvious: yards to kilometers. 5,000 yards is equivalent to about 3 miles, which would be just over 4 kilometers, since a kilometer is smaller than a mile. So that's our approximation. Looking at the conversion tables, we see we have a relationship for yards and meters, and SI prefixes will provide the meters to kilometer conversion. So our solution path will be yards to meters to kilometers. The conversion relationships are listed. The yards-meter conversion is not exact, but the one we're using has more sig figs than the initial given value, so we won't have to adjust it. Now we just plug in the ratios and finish up the computation. The initial quantity has 3 sig figs, so that dictates the sig figs on the final measurement. The value we obtained seems to be consistent with our estimate, something over 4 kilometers. The next example will utilize exponents and derived units. 35.6 feet cubed is how many milliliters? When I think about the size of a foot cubed compared to the very small volume that is a milliliter, I'm pretty sure we'll get a large value at the end of this computation. It's easier for me to think about this solution path starting with the endpoint. The only derived value I can find is one that relates centimeters cubed in milliliters, so this will have to be the last step. The rest follows easily from the conversion tables as we work backward. We follow the path from centimeters to inches to feet. Looking at the definition of the derived unit of volume, we realize that we must cube the unit and the relationship number. Ratios will reflect these cubed relationships. The final quantity should reflect 3 sig figs and is a very large value, just as we expected.
When we think about what we do in chemistry, we typically start off with a given substance, right? Run them through a reaction process and then turn them into other substances. In other words, we have a given state of matter, our beginning point, and then we see a change leading to a final state of matter, our end point. So you could say that chemistry in its most basic form is nothing more than a kind of multi-step conversion problem. Try to keep that simple idea of chemistry in mind as we march forward. Often we'll be faced with a problem that at first glance seems to be overly complex. But focusing on this simple picture of chemistry, along with our strategy of building solution maps, we can break the problem down into smaller, more manageable conversion problems. Okay, that's enough for now, and we'll see you in the next video.